secant x, I didn't say it was sine x over cosine squared. I said derivative of secant x is secant x tangent x. That's what I said. But you can see here that you can split this up if I wanted to, right? I could split this up into two pieces like this. If I multiply these back together, 1 times sine is sine, cosine times cosine is cosine squared. So that's legitimate to write it that way. And then what's that? Secant, and that? Tangent. So this is secant x tangent x, which is what I told you the formula was, right? You see how you could do this for all the remaining ones? Like if you want to know derivative of cosecant, you would put 1 over sine. If you wanted to do cotangent, you would put cosine over sine. And if you do all the algebra for those, you would get those answers that I gave you on that sheet. Okay? So the quotient rule is very powerful, because you can use it to find derivatives of a lot of different things. All right, let's do this one. This one looks really interesting to me. If y is equal to x sine x, find y35. We did one like this a couple of classes ago where we found the 99th derivative of sine. Do you remember that? We had to establish this pattern. This is different though. What's different with this? You've got multiplication. It's not just sine by itself, right? It's x times sine x. And this is going to look like, well, it's going to be pretty bad. Let's see what happens. All right, let's just find the first derivative. What would the first derivative be? So I need to apply which rule to this? Product rule, right? I have my product happening right here. This is like my f and this is like my g. So take a moment. Get your product, multiply it out, see what or use the rule, see what you get. It should take you maybe 1 minute to do that first derivative. If you're there, raise your hand so I can see where everyone's at. Okay. You good? Okay. Everybody get that? Anyone have any issues with that? Want to talk about it? That would be your first derivative. Now, if you had to take the derivative again, you now have addition, don't you? So you could do these separately. When you do this one, the derivative is just going to be cosine x, no issues, right? But on this one, won't you have to do another product rule? Okay, go ahead and do it. So y double prime will be equal to I put the raw derivative up there for you, and then I'm going to clean it up, but let's just make sure everyone can get to that raw derivative. If you have a question, please raise your hand. I'm going to just walk by and help you out if you need it. I see some looks of like, okay.
Are we still doing the product rule for this?
So the first derivative is this one right here, right?
Yeah.
Yes, and we were done with the first. Now, because it's two terms, you do just derivative of sine, get cosine by itself, and then for this product rule, right? Yeah, it doesn't look like that's what you did. Okay. I think you treated that plus like it was a product or something. Okay, yep. Anyone else need a hand? Sure, y'all just being shy. What should my next line read? I'm not taking the derivative, I'm just cleaning this up. What should my next line read? How many cosines? 2 cosine x minus x sine x. Make sure everyone can agree with that. Yes? That's y double prime. So let me box this. This one right here, this was y prime, right? This is y double prime right here. And of course, y by itself, that was y. Yes? Yes? Okay, so see I only put the bracket here to stress that this was this product rule, right? This right here came from that derivative. Now, I can drop the brackets because this is addition, and it just goes plus here, and then this becomes a minus. But I have a cosine and a cosine added together, which gives me 2 cosines, right? I'm going to take the derivative again, a third time. I have to take the 35th derivative, okay? We're going to be here for a while. Y triple prime equals. Now, we're going to see a pattern established here in just a second. We're going to start to see a pattern. So what is derivative? We do these separately, right? Because there's a subtraction. Derivative of this would be what? 2 is a constant. It's attached, comes for the ride. So 2 is going to come for the ride, but then what's derivative of cosine x? Negative sine x. So this will be negative 2 sine x. That fair? Okay. Now, careful, careful. We have a minus, don't we? Minus. Now, I'd like for you to put like a bracket or something here so you can do your product rule on this one. You're going to do your product, and you're going to ignore the minus. Understand? The minus is going to come here. Ignore it. Do your product rule here. But wait a minute. Hold on. We did this derivative already. This was the original problem, wasn't it? And when we took the derivative of that, what do we get? That right there, right? So can't I just take that answer and slap it in here? Sine x. I mean, you could do the computation also, couldn't you? But we already did that work. And now let's clean this up. Can I drop these brackets? If I distribute the negative through, right? The negative would have to go through. So when I do this minus sine x and it joins up with this one up here, I'm going to have minus 3 of them. So my third derivative is minus 3 sine x. And then what's here on the outside still? I did minus to here, right? So minus x cosine x. Yes? This is the third derivative. I think I need to do at least one more derivative to see a pattern. There's my third. You ready for the fourth one? I'm going to try and squeeze the fourth one in right here. The fourth derivative, so I'm going to start writing the number in here. This will be equal to, I need to take the derivative of this, right? Separate from this. What is the derivative of this? Negative 3 cosine x. So I have negative 3 cosine x. And then a minus sign And then I'm taking the derivative of a product again. Does that look familiar though? X cosine x. Did we ever take the derivative of x cosine x? We did. It was right here, right? It was this piece right here. So I know that that's going to be minus in brackets cosine x minus x sine x. I'm running out of camera space here. But you see, it's just that piece cleaned up a little bit. I just put the x in front, change that to a minus. That's this piece. Then distribute the minus through. How many cosine x's will I have? -4 of them. Cosine x. And then what's out here? Plus, because this minus minus becomes plus, x sine x. All right. That was our fourth derivative. Does this seem like torture to you? It's not supposed to be. In Cal 2, you actually do have to do this. You have to find a formula. You actually have to find a formula for the nth derivative in Cal 2. All right. Do you see a pattern? It looks like, if we just look at the first derivative, right? We have a sine x. The second, and forget this. Just sine x, then it goes to 2 cosine x, then -3 sine x, then -4 cosine x, right? So it is switching between sine, cosine, right? Man, maybe we need one more. Can you guess what the next one would be? Okay, so hold on. Y fifth derivative would be equal to, you think it'll be -5? It's going to be +5 because derivative of cosine is negative, right? Yeah. Negative sign, and it's going to make that. So it looks like, look, we started off, this was the 0th derivative. Do you agree? And it was a positive. And then the first derivative was positive. And then, oh wait, hold on. No, take that, scratch that. This, I'm looking at the first term. Positive, positive, negative, negative, positive, positive, negative, negative. That's the pattern that we're going to have. So this one will be 5 what? Sine?
5 sine x.
Sine x. And then
Minus x.
the derivative of this. We've done that already? Right, it was up there. So what will we have out here? Plus x cosine x?
Yeah.
Okay. I've already put the things together to make the 5, to make up the 5. So it looks like we're getting positive sine, then +2 cosine, then -3 sine, then -4 cosine, then +5 sine, and then the next one should be what? Yes?
Positive 6 cosine.
Yes?
I have a question on the fourth derivative.
Yes.
On cosine, on the second part, why just subtract right there?
Right here?
No.
Right here?
Yeah.
I just took the derivative of this right here.
Yeah, but when you do that, you use the product rule.
Product rule, which is the same thing we did right here. So derivative of this is 1 times this, plus derivative of this, which is negative sine x, times x. And that's where that minus comes from. Yes? I'm not sure if y'all are getting the pattern or not, but let me write down the sixth one. Let's try and write the sixth one down. I'm not even going to look at taking a derivative. What would the sixth derivative be? Your guess would be 6 cosine x, 6 cosine x, and then minus x sine x. What would the next one be? Seventh derivative. -7 sine x.
Plus.
And then what do you have? Minus x cosine x.
-7 cosine x.
Let's see if we agree with this. I'm not sure I do. Look, this was a 1 here, right? We have sine, 1 sine, 2 cosine, both positive. Then we go -3 sine, -4 cosine. So +5 sine, +6 cosine, then negative 7 sine, then the next one would be negative 8 cosine. All right, that part I think we've got. Let's establish the second part. We have plus cosine x on the first derivative, minus x sine x on the second. On the third, minus x cosine x, and then over here, plus x sine x, and then plus x sine x. So are these switching?
Yep.
Look at these are switching. You're going negative, negative, right? And here positive, positive. Let's go backwards. Positive, positive, negative, negative, positive, positive. You see it here? The x sine x is like this piece. So it's almost like we had positive, positive, negative, negative, positive, positive, negative, negative, right? And then we'd have positive, positive. Okay. Can we figure out what the 35th derivative is going to be? You could do some sort of modular arithmetic on this. Here's what I could say. I could say on that 35th derivative that I know I'm going to have a 35 there, right? I don't know if it's positive or negative yet. I'm either going to have a sine or a cosine. What is it going to be? Can you tell? At the first derivative we have sine, second cosine, third sine, fourth cosine, fifth sine, sixth cosine, seventh sine. So all the odds we're getting sines, right? All the evens we're getting cosines. So this should be odd sine x. So do you understand? I'm still not sure if it's negative or positive exactly yet. What about that remaining piece? X cosine x. It's going to be, again, all the odds have x cosine x, don't they? All the odd ones do. So I know it's an x cosine x, but not quite sure about positive or negative, right? So at this point, I mean, there's several approaches you could use. I'm going to put right here plus or minus, question mark, that we don't understand that. Yes? All right? All right. Well, how do we figure it out? I'm erasing what I need to look at, so this might be troublesome. Here's one way we could do it. All right. Okay, this is the derivative, and then this will be the sine of just that first term. Okay, so when we had the zeroth derivative, you don't have that first term, right? So let's scrap that. On the first derivative, and help me out here, on the first derivative, that first term was what, positive? So it was positive, second was negative, positive again, right? Third and fourth were negative, yes? Fifth and sixth, positives. So it's just in groups of 2, right? So the question is, where does 35 land here?
Positive on the 5. But it's going to be repeating all the way up.
When would these repeat? When are we getting positives? We're getting positives at 1, 1, 2, 5, 6. When would the next ones come? 9, 10.
12, 13.
So what are you doing here? Here's the way I'm doing it. I'm saying I'm adding 4 to each of these. Okay? So 4 on top of 1 is 5. 4 on top of that's 9. 4 on top of that's going to give me what? 13 and then 14. And I can keep doing that, right? Do you remember how I showed you to do that last time? You start at 1 plus 4n. Does that equal 35? So if I start at 1, I keep on adding 4, am I going to land on 35? If I start at 1 and start adding multiples of 4, am I going to land on 35? The other one is saying 2 plus 4n equals 35. I'm just looking at these two. It's either 1 plus 4 plus 4 plus 4, or it's 2 plus 4 plus 4 plus 4. Yes? Do either of these, can you solve either of these for n and get an integer? So let's see, if I solve this one, subtract 1 on both sides, I get 4n is 34, right? There's no integer answer for this? You see what I'm doing or not? Yes? So there's no integer answer there. This one, if I subtract 2, I get 4n is 33. There's no integer answer for that, which means this needs to come from the other list, right? So it's got to be a minus. Now, hold on. Let's check something else. How could I do the same argument for these? What would I be checking here? 3 plus 4n and 4 plus 4n. Do those equal 35? So let's try that first one. Subtract, you get 4n is 32, which means n is 8. So it happens here. It happens in this list right here. So it's going to come out to be a negative out front. Now you could just count out 35, but so this will be negative. I'm not going to give you a test problem like this, okay? I'm not going to. But be warned, in Calculus 2, you have to be able to do this, all right? And it's not a bonus question or anything. I mean, you have to be able to, it's part of a bigger problem you're trying to do. Okay, what about the last part? So this one right here. So we'd have to go back again and establish the pattern of that second one. I've erased all my work, but maybe you can help me. I think it was a little different than this, wasn't it? Wasn't it different if I did another table? Help me out. You're looking at that piece that has either x sine x or x cosine x in it. When we take the derivative, I'm talking about that second piece. So at the zeroth derivative, it was positive, right? And then the first derivative, positive, and then it started switching, right? Negative, negative, and then positive, positive. But we already know, like, we can use the same sort of attack, can't we? But what would I use for my numbers here? 0, 1, 2, and 3. Because I'm going 0, 1, 2, and 3 to figure out what's happening with these. And if I solve these, which of them work? This one right here? We know this one works. So this will give you n is 8. So it's got to happen, it's got to be happening on the third one. It's going to be like this, so it's going to be minus also. I understand this is a stretch, okay? This problem is not simple. But I know some of you are getting this, and that makes it worth it. Won't test you on it. All right, I think that that's sufficient for this section. We're going to start chain rule. And again, I'm going to present the chain rule to you. I'm not going to prove it. So this is the next section, chain rule. Now, to get going on chain rule, I want to start out with go back and take a look at a couple things from college algebra. All right. Recall from college algebra what we called functional composition. In other words, this thing. Remember that notation? Fog, if your instructor told you like fog and Goff. Do y'all remember that? Okay, I never used fog and Goff, but f of g, what that meant. All right, so what this notation means is this. If you're given if you're given two functions, f of x and g of x, then the notation, I'm getting away from this black dot. This notation, f of g of x, means that you take f and inside of it you plug g. This notation means this. Now, as a specific example, let me show you a specific example of functional composition. As an example, I would like us to let f of x be equal to sine x and let g of x be equal to x squared plus 1. Then find f of g of x. I'm not doing any calculus right now. I'm recalling. I'm going back to college algebra. I'm asking you to remember how we did this. So what is it? How do we do this? We take f, and inside of it we plug g, right? That's what that means. You're going to take the f function, plug in g.
So you'll have sine x squared, parentheses, sine x squared plus 1.
Yep, we're taking x squared plus 1, right? That's g of x, and we're plugging it into the f function. So that means we're going to take the f function, replace all the x's with x squared plus 1. So this becomes sine of x squared plus 1. Right? Okay, that's what this notation means. We need to make sure we're all clear with what that notation means. Now we're ready to talk about the chain rule. The chain rule is how we take derivatives of functions that are composed with other functions. See, right now, if we have two functions that are multiplied together, we can do something. Product rule. If we have two functions that are divided, we can do that with quotient rule. X to various powers, we can do that with power rule. What we can't do yet, or no one has shown us how to do it, is take the derivative of something like this. See, this is not a product rule. Do you all see that? If I asked you for the derivative of this, this is not sin times x squared plus 1. Right? This is sine of x squared plus 1. And how do we differentiate something like that? And to do it, we need what's called the chain rule. This is probably the most important rule. You cannot live without the others, okay? Like you can't survive without product rule and quotient rule. Those are definitely important. But this one right here is kind of the big daddy when it comes to the rules of differentiation. And I would say the hardest to learn. It just takes some time to pick up on it, all right? So here's the rule. It says, if y is equal to some function composed with some other one, right? So that's fog, right? F of g of x. So if you're looking at something that is a function inside of another function, then y prime is equal to this. I want you to pay attention to where those prime marks are. Okay, that is the rule, and we are going to do an example right next to it so you can see how this rule works. So as an example, let's take the one we just had. Y equals sine of x squared plus 1. The derivative of this is something, right? So the way I'm going to do this is on the side over here, I'm just going to write down what f of x is and what g of x is. I'm just going to write it down. So which is which? Yeah, so remember, g is the one on the inside, f is the one on the outside. So the inner function here is what? X squared, that's my x squared plus 1, that's my g of x. In my outer function, sine x. You'll hear the language I'm using here. The outer function is sine, the inner function is x squared, right? According to the chain rules formula, which I'm giving you, what you're supposed to do is you're supposed to take derivative of outer function, right? Plug in into it the inner function, right? Take the derivative of the f, but inside of it, plug in the g, but don't touch the g. Don't differentiate it, okay? And then multiply it times what? Now, right, derivative of the inner. Multiplied. See? So let's see how this works. I'm going to take the derivative of the outer function, which, what is the derivative of sine of x? Cosine of x. But I'm not going to write cosine of x. I'm going to do cosine of what? Of the inner function. So the inner function inside of the derivative. Do y'all see that? That's the derivative of sine, which is cosine, and I'm just plugging the inner function back into it. Then I say times now the derivative of the inner function, which is just 2x. And then this becomes 2x cosine of x squared plus 1, because I can move the 2x out to the front. Y'all see that? We obviously need to do another example. I'm going to do one more example, and then I'm going to show you the way that I do it, all right? This is the way the book does it, and it's fine, but I have a different way, kind of a different way. All right, ready for another one? Okay, let's do this one. This one's going to be a little harder. Let's do y equals tangent to the fourth x. We want to find y prime. Do you have composition here? Do you have a function inside of another function? If so, what are they? What are the functions here? My hint to you is that yes, you do have something. Think about this in terms of order of operations. If I gave you a value of x right now, where would it go first? If I said, hey, plug this in for x, what would you do first to that x? No? No? That's what that means, right? So if I gave you an x, you would first take tangent of that, wouldn't you? And then after you're done with that, you would do the fourth power. So isn't that fourth power like the outer function? The inner function would be the tangent. Understand? So couldn't I put tangent x here and then x to the fourth there? That's kind of weird, but that's what it would be. Because if you took this and plugged it into that, wouldn't you get this? Y'all see that? Your outer function is a power function. I feel like I lost y'all there. Y'all okay? Yeah. Pass that around, please. Sign in. Does anybody have a sacrificial piece of paper that I won't return to you? You got it ready? Okay, hold on. We already got one. Sorry. Go ahead. Everybody, this is going to come around. Put your name on it. All right? And make it legible so I can read your name. Pass it around. You're going to get a quiz grade today for being here. That doesn't happen often, so take it, all right? Just make sure your name's on that piece of paper. Hey, hold on now. This right here. I'm supposed to now, to take the derivative, I'm supposed to take the derivative of the outer function first, which is, what's the derivative of this? 4x cubed, right? But I'm not going to do x cubed. I'm going to do what cubed? Tangent. Okay, so that's the outer function. Derivative of that's 4x cubed. However, I'm going to not plug x into it. I'm plugging the inner function into it. So when I plug tangent in, I get this. Then times, now, just the derivative of the inner function. So derivative of tangent x is secant squared x. And the most you could do with this would be 4 tangent cubed x times secant squared x. You could just rewrite that, because this notation, we never use this notation. With the parentheses in the cube, we always use this notation. All right, I've got 5 minutes. I'm going to show you the same two problems, a different approach. And I'm not showing you more than one approach because I'm trying to confuse you. It's just that different people see it different ways, and it makes more sense different ways. So let's look at this one. Y equals sine of x squared plus 1. All right. Some people like this, some people don't. So let's see what you think. All right. I want to take the derivative of this. So what I'm going to do is I am going to have to realize I do have composition. I have a function inside of another function, right? What is the outer function here? Sine. Sine of x. Well, sine, right? The sine function. So what I'd like you to do is just squint your eyes. And there's an eraser, right? So I have sine of an eraser. What is the derivative of sine of an eraser? Cosine of an eraser. Not cosine of x, cosine of an eraser, right? So let's write down here cosine of an eraser. But what's the eraser? X squared plus 1, right? Okay, so what I've done is, looking at this chain rule so far, I've done the outer function. I've taken care of that, haven't I? I've differentiated the outer function. So I'm just going to kind of scrap it off like that. Now I'm going to take a step inside to the next function I see. And the next function I see is what? X squared plus 1, which I'm not afraid of. That's just a little polynomial. And the derivative of that by itself would be what? 2x. So I just say times 2x. And I get the same exact result that I had earlier. Does that kind of make sense? Let's go back to this one. If I look at this one, get all that crap out of there, I have an eraser to the 4th power, right? What is the derivative of an eraser to the 4th power? 4 erasers to the 3rd power. What's the eraser? Tangent x. With me? Now, I'm going to move this out of here. I've taken care of that power. I've differentiated it. So I move inside to tangent. And I say, what's the derivative of tangent? Secant squared. So I always, with chain rule, multiply by secant squared x. Get the same answer. I'll do one more because I have 2 minutes. See if you really kind of get this. Watch. I want to do sine of cosine of sine of x squared plus 1. Kind of throwing you right into the fire here now. Okay, you see that? There's no products happening there. That is all composition, but that's more than just f of g of x. That's like f with g with h with k. It's like 4 functions composed. So if you were trying to figure out what the outer function would be here, what would the outer function be? Sine, right? This sine right here. Then inside that you have another cosine, and then inside that a sine, and then inside that here. So if you look at this like a layered onion, like this is the inside of the onion, these are the layers on the outside. I'm going to start on the outer layer, okay? And I have here this nasty old cloth. So we have sine of a nasty old cloth, right? So the derivative of sine of a nasty old cloth is what? Cosine of that nasty old cloth. So it's going to be cosine of, now it's important that you actually remember what the nasty cloth was, which was everything underneath it, right? So what is that? Cosine of sine of x squared plus 1, close, close, close. Hold on, let's see if I have enough parentheses here. Close, close, close. That's it right there. Right, 3 parentheses this way, 3 parentheses that way. Okay? Questions? Not done. I've just done that outside layer. Now what I'm going to do is I'm going to move inside to the next layer, which is approximately cosine of this mouse pad. That's a mouse pad. Okay? Cosine of that mouse pad. The derivative of cosine of a mouse pad is what? Negative sine of the mouse pad. So I'm going to put here times. Why times? Because that's chain rules always times. I'm going to have a negative here. So to be safe, I'm going to put a parenthesis in front of it. Negative, you said it was negative sine, yes? Of what? This mouse pad. And what was the mouse pad? Sine. So I've got sine of x squared plus 1. 1, 2, 1, 2. I know this looks bad. There's my mouse pad, right? Negative sine of my mouse pad. This was cosine of that dirty cloth. Okay, I'm not done. I've just taken care of cosine now, right? So now I move in, times again, and now I'm taking the derivative of this, right? Sine of whatever. Running out of things here. Sine of this marker, okay? Sine of the marker. Derivative of sine of the marker is cosine of the marker. So cosine of the marker, x squared plus 1. So I've taken care of the sine. Now I go inside again. Times 2x, finally. That is the derivative of that composition. See it? Do you see why they call it chain rule? I mean, you're kind of like working through this chain. Do your homework for the section on product rule and quotient rule. We will do a lot more chain rule later, and they will get pretty... This was pretty nasty, all right? This one was, but they... Have a good day. We'll see you on Wednesday. Everybody signed in. Everyone put their name on that sheet. Take that.
Is the proof of the chain rule ugly too?
It is also pretty ugly, yes. Actually, the quotient rule is better than the chain rule. Chain rule is hard. Yes.